Nicholas and Kevin set up the circuit represented below. The battery has an internal resistance R and an EMF of 12 volts. Voltmeter V1 has a reading of 4 volts. Calculate the resistance of the external circuit. Money for jam marks, 1 over R parallel is equal to 1 over 6 plus 1 over 6, which is equal to 2 over 6. But that's not R parallel. R parallel is equal to 6 over 2, which is 3 ohms. So this has an equivalent resistance of 3 ohms. If I then add in the 2 ohms, the R external is equal to 3 plus 2, which is equal to 5 ohms. Now lots of you have just gone and put in a step over here, plus 2 ohms equals 5 ohms. This equal sign means something. It means that you have to be equal. And people are going to penalize you if you say that 3 ohms is actually equal to 5 ohms. It's not. It's like 3 rands equal to 5 rand. It's not the truth. When you're going to put in another piece of information, you need to start on a new line. Calculate the reading on the ammeter. So we've got information around this particular resistor. So I'm going to say I is equal to V over R, and it's 4 over 2, which means that my ammeter is going to be reading 2 amps. And calculate the internal resistance of the battery. There are a few different ways of doing this, but I would have said, so what is R total? R total is equal to V over I, which is 12, the EMF, over the series current, which is 6 ohms. And I know that 5 of those ohms come from the external circuit, so R internal is equal to 6 minus 5, which is 1 ohm. In the photo mixer, the microwave and iron are all connected to the same multiplug. Below is a circuit diagram. The fuse will blow when it exceeds 15 amps. Calculate the resistance of the mixer. So the first thing that we're going to do is we're going to say I know the potential difference and the power of the mixer. So I'm going to say power is equal to V squared over R, which is 440 is equal to 220 squared over R, and R turns out to be equal to 110 ohms. Caleb wishes to establish if all 3 appliances can be used simultaneously. Use applicable calculations to determine the multiplug circuit, if the multiplug circuit will be able to run all 3 appliances at the same time. So I'm going to get the current on the top branch, the second branch, and the third branch. Good news, third branch already has a current. Top branch, not terribly difficult. I'm just going to say power is equal to V times I, and therefore it's 440 divided by 220, so I is going to be equal to 2 amps. Then I have 132 kilowatts, 1,32 kilowatts, so that's 1,320 watts. And if I'm going to now work out power is equal to V times I, so substituting, I'm going to say 1320 is equal to 220I, and I find that the current in this one is equal to 6 amps. So I then see what everything is added together, and I'm going to go 2 plus 6 plus 4 equals 12 amps, which is less than 15 amps, and you need to draw that conclusion. You can't expect the examiner to work it all out for you. Right, last one, the iron is used for an average of 2 hours per day. What is the cost of electricity used per day? So we want per day. We're not going to be multiplying anything further than that. If the average cost is given, give the cost in rands and cents. So we're going to say work done is equal to power times time. The power of the ion is 880 watts. I had to work that out. Power is equal to V times I, which is equal to 220 times by 4, and that's going to be 880. Now if I'm working, that's watts. If I'm working in cost, I need to work out my energy in kilowatt hours. So my power must be in kilowatts, 0,88 kilowatts, multiplied by the number of hours, 2 hours every day, and I land up with 1,76 kilowatt hours each day. Then I'm going to say, but how much does that cost? 1,76 kilowatt hours at 116.63 cents Turns out to be 205 cents, but that's not what they asked for. They wanted rands and cents, so it's 205. Now we are going to go into electrodynamics, briefly discuss one advantage of the use of low current for the transmission of electrical energy through the national grid. If I have low current, I will have less heat as the electrons, because there's less electrons, so it's less electrons, therefore less electron movement, if you like, and therefore less energy gets lost to heat. So we manage to save or retain as much of the power as possible because we're not losing energy. The diagram below shows the transformer and rectifier can be set up to convert 220 volts of alternating current into 11 volts of direct current. The primary coil has 1000 turns and the current in the primary coil is 0.05 amps. An AC generator is used to provide the current to the primary coil. State 3 ways in which the EMF that is induced in the generator can be increased. So we're trying to increase a generator. Now a generator makes current, so I can't say increase the current. What I need to say is more coils for the generator, stronger magnets, and finally I could move it faster. Name the type of transformer given over here. We are moving from 220 volts to 11 volts and therefore that is a step down transformer. Briefly explain why alternating current is required for transformers. In order to induce a current, so to induce a current, you must have a change in magnetic flux. And alternating current is always changing with both strength and with direction. So you land up with the change that you need for the induction of current. Calculate the number of turns in the secondary coil of the transformer described above. So now we need to do a number of turns. So number of turns is NS over NP is VS over VP. They've given me the VS is 11. They've given me the VP is 220. They've given me the number of turns on the primary is 1000. And it turns out when you rearrange that, NS turns out to be 50 turns. Assuming 100% efficiency, determine the alternating current produced in the secondary coil. So now we're going to go VPIP is equal to VSIS, and we're going to go 220, 0.05 is equal to 11, and what is the current in the secondary coil? And my current in my secondary coil turns out to be 1 amp. What is a diode? It is a component that allows current to flow in one direction only. Using the letters on the diagram, which we can't really go back to now, but anyway, indicate the path taken by conventional current in the circuit where P is positive. So we need to, conventional current flows from positive to negative. So you start with P and you end with Q, and you find that it goes through PLR, then it goes through the component, and then it goes through SMQ. 4 graphs below show possible readouts for an oscilloscope. Give the number of the graph that would be observed on oscilloscope G's screen. Oscilloscope G in the diagram is simply the incoming alternating current. So that's going to be going like that. So that's your graph 4. Simple as that. Give the number of the graph that would be observed on oscilloscope H. Well, oscilloscope H makes sure that current only flows in one direction. So it will either be going through PLR SMQ or the exact opposite way, but in both cases it comes out in the same direction on the other side at the load. So that is going to be graph number 2. The diagram below represents a simplified sketch of an electric DC motor. Name the component which ensures continuous rotation of the motor. Some people will say that it is the split ring commutator, but actually it's these brushes that allow for free rotation, so the carbon brushes. Name the part of this motor which becomes an electromagnet when the current flows in the motor. So we are going to land up with an electromagnet in the coil. So this is where you're going to land up with a moving electromagnet, and that it causes the, it becomes an electromagnet which interferes with this magnetic field, and that causes the movement. So it is the coil. In which direction will the motor spin, clockwise or anti-clockwise? You can choose either side, but I'm going to go around from here. I'm going to go in, and I'm going to say my current is going up over there. I need my left hand. I'm going to point my first finger from north to south. My second finger is going to go up over there, and what I notice is that my thumb is going downwards. So if my thumb's going down, that side's going down that way, and that side's going up, and that is a clockwise motion. Name the law that you use to find. It is going to be Fleming's left hand motor rule. Because it's for a motor. What property of the carbon graphite brushes makes them suitable for their role? Well, firstly, they are flexible, so they'll allow for the rotation, but also they must be able to conduct electricity. I mean, that's the biggest and most important thing about them. When the electric motor is connected to a 12-volt DC supply, it draws a certain current. The motor is now used to lift an object of a certain mass through a vertical height of 0.8 meters at a constant speed in 3 seconds. Calculate the percentage power efficiency of the motor. So I'm going to work out two different powers. The first one is, what is the electrical power output here? Its power is V times I. I know that it's 12 volts, and I know it's drawing a current of 1,2 amps, and that means it's 14,4 watts. That is the input. The output is going to be, what did it actually do? And power is equal to work done divided by time, and in this case we're moving through a height, so it's a gain in potential energy divided by the time. So it's the mass of the object, 9,8, the height it moved through, divided by the time, and I land up with 4,18 watts. I then need to say, if I'm looking for percentage efficiency, what did I get versus what was the maximum possible? So 4,18 divided by 14,4 times by 100 is equal to 29,03%. The battery is now removed and replaced with a voltmeter, and the coil is spun manually. In other words, I've just changed that motor into a generator. What kind of machine is it operating as now? It is a generator. And explain why the voltmeter reading increases when the coil is spun faster. There is more cutting of magnetic field lines. And if you want, you can use the word, there's more change in magnetic flux or magnetic flux linkage.